Have you ever stopped to wonder about the invisible physics happening every time you cook? Well, today we're firing up the stovetop to explore exactly that. Welcome to Thermodynamics, the hidden laws of your kitchen. So, let's jump right in with a classic kitchen mystery. Why on earth does a pressure cooker get food cooked so much faster than just a regular old pot? Is it some kind of kitchen magic, or is it pure physics? Well, the secret, it turns out, is all about thermodynamics. We're about to explore the fundamental rules that run the entire universe, and we're going to start right there on your kitchen counter. To really understand how a pressure cooker works its magic, we first have to get a handle on the most basic, number one rule of energy. And here it is, the first law of thermodynamics. Think of it like a super strict accounting rule for the universe. You can't just create energy out of nothing, and you can't make it disappear. You can only change its form. The equation you see is just how scientists write it down. Delta U is the total energy, Q is the heat you add, and W is the work that the system does. I love this analogy. It makes it so much easier to understand. Imagine energy is like a bank account. The total internal energy, that delta U, that's your account balance. Adding heat, or Q, is like making a deposit. And when the system does work, like steam pushing up the lid of a pot, that's a withdrawal, or W. Simple, right? The energy books always have to balance. Okay, so now let's look at a special case of this law, one that's going to be absolutely crucial for understanding our pressure cooker. This is called an isothermal process. The name kind of gives it away, right? Iso means same, and thermal is all about temperature. So it's simply a process where the temperature stays perfectly constant from beginning to end. So check out the logic here. If the temperature doesn't change, then the internal energy, our bank balance, remember, it also stays the same. So delta U is 0. This means any heat you add, Q, is immediately used to do work, which is minus W. It's like a deposit that instantly becomes a withdrawal. So the big takeaway is that in an isothermal process, energy flows in as heat and flows right back out as work. It's a perfect conversion. And this is a really fundamental idea for understanding everything from engines to, you guessed it, pressure cookers. Okay, we've got the rules of energy down. Now how does this actually solve our pressure cooker mystery? Let's connect the dots. This chart lays it all out perfectly. If you're on a mountaintop where the air pressure is low, water actually boils below 100 degrees Celsius. But inside that sealed pressure cooker, the pressure is incredibly high, and that forces the boiling point of water to go above 100 degrees. And hotter water means faster cooking. It's that simple. But why does pressure change the boiling point? Well, you can imagine that high pressure is literally pushing down on the surface of the water. It's making it a lot harder for those water molecules to escape and become steam. To make that jump, they need more energy, and that means a higher temperature. And the energy needed for that jump is enormous. It takes a huge amount of energy, 535 kilocalories to be precise, just to turn liquid water into steam, even without raising the temperature. That's the huge energy cost we're talking about, and it's what makes steam so incredibly powerful. So we've solved our kitchen mystery. But the laws of thermodynamics have implications that are way bigger than just cooking. They govern the entire universe. This brings us to the second law of thermodynamics, which is honestly one of the most profound principles in all of science. It tells us that the universe is constantly and irreversibly moving in only one direction. And that direction is toward greater entropy. So what's entropy? It's really just a scientific measure of disorder or randomness. Think about it. Tidy rooms naturally get messy, ice melts into a puddle of water, the universe just naturally moves from order to chaos. Here's the perfect example. A hot cup of coffee will always cool down as its heat spreads out into the room. The reverse never happens. You will never see a cool cup of coffee spontaneously start boiling by sucking heat out of the air. That would completely violate this relentless march of entropy. And this brings us to a final, pretty profound question. If the universe is always moving toward chaos, how is something as incredibly complex and ordered as life even possible? How can a tree, a single cell, or even you exist at all? Now that is something to chew on.